Hi guys, welcome all of you. This is Reena V. George from RVGMATHS and Talents. Already we have started chapter 1, real numbers. This is part 4. Here we are revisiting irrational numbers. Let us just brush up what is irrational numbers. Before that, we just revise rational numbers. Okay, what is rational number? Do you remember? Rational numbers are numbers that can be expressed in the form P upon Q, where P and Q are integers and Q not equal to 0. Okay, you remember that? Okay, that means we can express every rational number in the form P upon Q. This P and Q are integers and Q not equal to 0. Denominator is not equal to 0. So that are rational numbers. For example, you can say all integers are rational numbers. If you take any integer, for example 7, it can be expressed as 7 upon 1. Okay, 7 upon 1. Then it is in the form P upon Q. That's it. Then it is a rational number. Then what are irrational numbers? Do you remember? Irrational numbers are numbers which are not rational numbers are called irrational numbers. And we know root 3, root 2, pi, etc. are examples. Is it? Or you can say irrational numbers are numbers that cannot be expressed in the form P upon Q, where P and Q are integers and Q not equal to 0. Then if you take any prime number, for example 70, it's a prime number, you know. Then if you take root 70, then it will be a prime number. Another example, can you say? Root of 23. Is it? That is also an irrational number. That means if you take any prime P, then root P is irrational. That's an example. Okay. In this chapter, we are doing one theorem, theorem 1.2. Let P be a prime number. If P divides A square, what is A? A is a positive integer. When P divides A square, then P divides A. That's the theorem. Let me explain once more. P divides A square. That implies P divides A, where A is a positive integer. Okay, and P is a prime number. How can we prove this? Let us see. Then here we have seen that A is a positive integer, and we know we can factorize any positive integer into prime factors. Is it? Let this be the prime factorization of A. That means A equal to P1, P2, P3, etc. Pn. Where P1, P2, P3, etc. Pn are prime numbers. Okay, and they may not be distinct. That means, see, for example, we are factorizing 12. 12 can be factorized like this: 2 times 2 times 2 times 3. Is it? That means that is equal to 2 square times 3. So here 2 is a prime factor, 2 is a prime factor, 3 is another prime factor. Then you can say P1, this is P2, this is P3. Like that. Is it? Then here you can see P1 and P2 are not distinct. Is it? So in the same way you can say these P1, P2, etc. Pn are not necessarily distinct. Okay. So we are factorizing A like this. Then what is A square? A square is P1, P2, etc. Pn times P1, P2, P3, etc. Pn. Is it? That's okay. You understood that. Then you can write like this. Here we have written like this. No? Same way you can write P1 square, P2 square, etc. Pn square. Okay. See, in the theorem, we are given P divides A square. And we have to prove that P divides A. Here we have seen that A square is P1, P2, P3, etc. Pn whole square. Is it? Then we are given in the theorem that P divides A square. That means P divides this P1, P2, P3, etc. Pn whole square. And we know all these are prime factors. By the uniqueness of fundamental theorem, we can say A square can be factorized only in this way. That means this factorization is unique. Is it? So, all prime factors are included in this. Is it? That means P divides A square means P being a prime factor of A square, P is included in this list of prime factors. Is it? That means P is one of these prime factors P1, P2, etc. Pn. Are you following? P is one among these prime factors. Okay. We started with that A equal to P1, P2, P3, etc. Pn. Is it? A is a product of these primes. And we have seen that P is one among them. That means from that you can say P divides A. Is it? Have you got it? So P divides A. So what we got? P divides A square implies P divides A. So that is a theorem we have to prove here. Is it? See this. P is one of the prime factors of A square. By uniqueness of fundamental theorem, P is one of these P1, P2, etc. Pn. Since A is this, A equal to P1, P2, P3, etc. we say P divides A. Okay. Hence the theorem. So we got this result. Then come to the next theorem. Theorem 1.3. Okay. What is it? Root 2 is irrational. Okay. Already we know that root 2 is irrational number. We have seen that. But here we are proving it. Understand? Root 2 is irrational. That is what we are going to prove here. Okay. Let us see. Here we are considering a method of contradiction. See, let us assume to the contrary that root 2 is rational. Okay, we have to prove root 2 is irrational, but we are assuming that root 2 is rational. Okay, so we can write root 2 equal to r upon s, where s not equal to 0, r and s are integers. You know that, is it? If root 2 is rational, we can write like this. And here suppose r and s have common factors other than 1. Then we can cancel that and we can simplify it and let us write like this. Root 2 equal to a upon b. Then you can say a and b have no common factors. That means a and b are coprime. You know what is coprime? Coprime means two numbers are coprime, means they don't have common factors. And that means their HCF is 1. Is it? For example, 2, 3, 4, 9, 5, 7, 9. All these are coprimes. Their HCF is 1. So here we can see root 2 equal to a upon b, where a and b are coprime. That a and b have no common factors. Is it? Then This can be written as root 2 upon 1. Is it? Then we can cross multiply this. Then we can write this as b root 2 equal to a. Have you got it? Okay. Then we are squaring this. Squaring on both sides. What happens here? B square root 2 square is 2. Is it? B square times 2 equal to a square. Okay. Then you can rearrange this. You can write this as 2b square equal to a square. Have you got it? You just observe this. 2 times b square is a square. That means from this you can say a square is even. Is it? Because it is 2 times a number. That means 2 divides a square. You can say like that. Is it? Then the theorem we have just seen that 2 divides a square implies 2 divides a. Is it? That theorem 1.2. We have seen just now. That means 2 divides a square implies 2 divides a. That means a is also even. A is even, or you can say 2 is a factor of a. Is it? 2 divides a. Okay. That means you can write a equal to 2c, where c is an integer. Already we got this. 2b square equal to a square. Here instead of this a, we can substitute 2c. So what you will get? 2b square equal to 2c whole square. That means 2b square equal to 4c square. Okay. Then you can simplify this, or 2 can be cancelled. Then you can write this as b square equal to 2c square. That means b square is divisible by 2, because b square is even here. Is it? That means 2 divides b square. We got 2 divides b square. Then we will get 2 divides b by the theorem 1.2. Is it? 2 divides b means b is also even. B is even. That means 2 is a factor of b. Is it? See this? Not this. Already we got a is even. Okay. Now we got b is even. Is it? That means we are getting a and b are even numbers. That means a and b have common factor as 2. So what you got? 2 is a common factor of a and b. That means we are getting a contradiction. Is it? We supposed or we started with a and b are co-prime. Is it? A, b are co-prime. That is what we started. But here we are getting a and b have common factor, and that is 2. So we are getting a contradiction here. Why we got a contradiction? Because our assumption was wrong. Our assumption was root 2 is rational. That assumption is wrong. So we can say root 2 is irrational. That means we have proved that root 2 is irrational. Have you understood this? See, we have done the steps here clearly. So our assumption as root 2 is rational number is wrong. So we can conclude that this root 2 is irrational. Okay. Have you all understood this? Okay. So let us see in the next class. Thank you for watching. Okay.